So let's now get into graphing some more parametric equations here. Let me see if I can focus this a little bit better. Maybe that'll be good there. So here I have a set of parametric equations, and again, my parameter here is t, and I want to sketch the graph. So I'm going to do it from the set of parametric. Sometimes you'll see the parametric equations kind of wrapped in these brackets. So that doesn't mean anything other than like, hey, they're kind of stuck together. This is my set of parametric equations since x and y are being defined separately. And I am going to go back to basic algebra class, back in the day when you were in Algebra 1 and you had to graph an equation. The easiest thing to do is make a table of values. Now, back in the day, you did an x and a y, and you had your columns, and you made up an x, and you evaluated for y, and you could plot those ordered pairs. And I'm going to use that strategy even though we have more variables here. This is, my parameter of t. I can independently decide what t is and evaluate for x and evaluate for y. So I'm going to utilize that. And you can either set it up vertically or horizontally. So I'm going to set it up in a horizontal format. So I'm going to make up t values here. I'm just going to make stuff up. And you know what? I'm going to go back to my Algebra 1 teacher always said, like, oh, do some negatives and some 0 and some positives. And there's certainly no reason for that other than try a bunch of things, see what happens. So I can decide what I'm going to plug in for t, whether it works or not. I don't know. We'll see. I'm going to evaluate for x and evaluate for y. All right, so I'll just kind of make my little table here. It doesn't look so great, but that's okay. And I'm going to plug into each one. So let's color code a little bit just to make it nicer. I don't know. Here's my x equation, and maybe change this one. Let's do our y equation. So you know, like what you're plugging into. You know, if t is -2, well then x is going to be -2 minus 3, which is -5. And if t is -2, then y is 5 minus 2 times -2. Well, that's 5 plus 4, so that would be 9. Get my color code. So that means when t is -2, I have an ordered pair of -5, 9. Now, unfortunately, that does not fit on the grid that I have here. So I'm going to keep motoring through and evaluate these. And you can go in any order that you want to. If you want to go straight down for all the t's, or you want to go straight across, maybe I'll do that. Maybe I'll evaluate all the x values. When t is -1, x would be -4. When t is 0, x is -3. When t is 1, x is -2, and when t is 2, x is -1. So now I'll kind of slide over and do the y's. You're just plugging into each one. So let's see. Y would be 5 minus 2 times -1. That's 7. Next here, right, I have 5, and we kind of see where we're going here. And now I'm going to see if I can plot these ordered pairs. So I couldn't plot -5, 9, but I think I can plot -4, 7. And then I've got another ordered pair, -3, 5. I'm just plotting each of these x and y's that, you know, they combine as this ordered pair. -2, 3. -1, 1. We see the path that we're developing here. And you could keep going, but I think I'm pretty good at recognizing, I think I could predict the next one, right? You kind of see a slope of -2 taking shape here. So I'm just going to draw the line straight down. And notice here I put an arrow in that direction. Normally when you're in Algebra 1, you would put an arrow in the other direction at the top. I am not going to do that. I am only going to show my orientation in one direction. This is a one-way road, because I plotted all these ordered pairs, and so at each step along the way, we had a different t value. This was where t was -1, and t is 0, and t is 1. So as time, think about it like that, kind of moves forward, my path is sort of heading in this direction. So your graphs are always one-way roads. You have to decide and indicate on your graph to make sure that you're showing the orientation of a parametric equation. That's not something that you did in any of your other math classes. You weren't graphing parametric equations. Now you are. So we should do that. Now, a lot of times you're going to be asked, hey, take this set of parametric equations that you have right here, and let's see if we can convert it to a rectangular equation. So let's convert to a rectangular equation. That just means a regular, like, equation that involves x and y. You're going to eliminate the parameter, essentially. Sometimes you'll see that, like, eliminate the parameter in the set of parametric equations. You're converting it to a regular equation that you're used to seeing, right? So there's a couple of strategies that you can do, but I like that phrase of eliminating the parameter. You have the skills from your past math classes to be very efficient at this. So what I'm going to do, this is very vague, but I am going to solve for t in one of the equations. It doesn't matter which one. And when I solve for t, then I'm going to substitute it into the other equation that I didn't use. So I think out of these two equations, it's much easier for me to say, you know what, instead of saying x equals t minus 3, let's just move that 3 over to the other side. I can equally say x plus 3 equals t. Right? I just kind of moved that 3, and now I have an expression for what t is. That's going to help me eliminate the parameter, because if I work on that bottom statement, right, like y, well, y is 5 minus 2 times t. I don't want the t there. What do I want? I'm going to eliminate the t. I'm going to replace t with what it legally is, x plus 3. You have successfully, right here, eliminated the parameter. I should clean it up and make it look nicer. Right? And so the rectangular equation here is negative 2x minus 1, which I think that's pretty convincing here. We already knew that the slope was negative 2. That kind of came out. And I can reasonably say, hey, yeah, that y-intercept is negative 1, so looks pretty good. And there's no reason it can't, go further up here. That would just be more negative time. Even though that kind of sounds weird for me to say, but t more negative would get you up here. And as t gets more and more positive, you're kind of headed in this downward direction. All right, so that's graphing a set of parametric equations. So let's go down to this next example, which I know usually terrifies people because anything with trig is automatically weird. So we're gonna plot it. And I do have my parameter here as theta instead of t. You could easily see x equals 3 cosine t. They just chose to use theta, so no big deal. So I'm going to set up my table of values in the same way. So that strategy you learned way back in Algebra 1 is still really helpful. If you ever need to graph anything, I don't care what fancy math class you're in, you could always do point plotting if you're really stuck. And I think here I'm going to use nice unit circle values because I want things that are friendly, not pi over 12, I want things that are friendly for me to evaluate into. So unit circle values, those standard special angles are really good to use. So I'm going to go with that. And again, I'm gonna go ahead and kind of look at this and say, well, let's look at the x equation, right? And then let's look at the y equation, and let's see if we can graph them. So again, you can kind of go x and y together, or straight across with the x and straight across with the y, whatever you want. You're just making up theta values, plugging them into each of those equations, and seeing what you get. Okay, so the cosine of 0 is 1, so 3 times 1 is 3. That's my first x coordinate. And I'll go straight across here. Handling the x equation, pi over 2. 3 times the cosine of pi over 2, the cosine of pi over 2 is 0, so 3 times 0 is 0. 3 times the cosine of pi, let's be careful, the cosine of pi is negative 1, so 3 times negative 1 is negative 3. And the cosine of 3 pi over 2 is a 0 again, so 3 times 0 is 0. And at 2 pi, we're kind of back where we started. Cosine of 2 pi is also 1, so 3 times 1 would be 3. And then I'll dig in here and handle all the y values. Same thing with the 4 sine of theta. So sine of theta is, sine of 0 is 0, so 4 times 0 is 0. Sine of pi over 2 is 1, so 4 times 1 is 4. And so on and so forth. I can get all of these values just by really knowing my unit circle values and being able to execute these. Okay, so I'm going to graph all of these ordered pairs. So now that I have all my parameters evaluated for the x and the y, really, these are all ordered pairs on your graph, like no doubt about it. I'm going to graph the ordered pair 3, 0, 0, 4, negative 3, 0. You kind of see where we're going. These are all like points in the rectangular system that I'm going to end up graphing. So 3, 0 is right here. 0, 4, negative 3, 0, and 0, negative 4. Right? So there are my guys. And I could plot other nice special angles like pi over 6 or pi over 3, but I think this is good enough for me to draw my shape. This is where we started. This is theta equals 0, and then we kind of went up here. So that actually, I'm just going to kind of connect the dots. This is a curvy graph, and I'm going to go ahead and put my orientation on it. You really only need to write it once. This indicates like, okay, I'm starting there, and then I move in this fashion through. If you want to do more of your orientation bars, you certainly can. You need something to indicate, hey, which direction are you traveling on this shape? Again, this is not a function. This is a nice graph. Okay, so what I'd like to do is convert this to a rectangular equation. Now, again, it's not a function. It's not y as a function of x because it fails that vertical line test. But you should be able to, on this graph, write its rectangular equation. And if you really take a blast from the past, the term for this is an ellipse. Let me spell it correctly. So there is a rectangular equation that describes the graph of an ellipse, and we're going to do it. And we're going to do it in a slightly different way. For trig, what I'm going to capitalize on here, I'm going to take a look at my my equation. See if I have, like, one of the parametric equations involves cosine and the other involves sine. And I know that there's a really good identity from trigonometry that I am going to invoke here and remind myself of. And that's this, that sine squared plus cosine squared is 1. What I think I'm going to do is write that in a different way over here. I'm going to write what the squared means. It means you're taking the sine of theta and you're squaring it. And over here, you're taking the cosine of theta and you're squaring it. I am going to kind of make this set of parametric equations fit into this true statement. This is an identity, which means it's true all the time, no matter what. So I just wanted to kind of rewrite it from the square being there to what it actually means in better notation here. So let me just clean that up a little bit. There. Okay. So what I'm going to do is come back up here and I will solve each one of these. I want to try to make this, to rewrite it to just say cosine. That means I want to ditch the 3. So x over 3 is my replacement for cosine. And I'll do the same thing here with the sine, right? I want to get the sine all by itself. So legally that would mean y divided by 4 is sine. These are going to be great swaps now to put into my equation. So let me go to a color that might stand out a little bit better with orange, right? I'm going to put x over 3 in for cosine. I am going to put y over 4 in for sine. And really right there is my rectangular equation. You have successfully eliminated the parameter of theta, and you have an equation in front of you that is only in terms of the x and y variable. This to me is okay. I think that's great. You may want to clean it up and write it like this. And hopefully you recognize that is the form of the equation of an ellipse, back from your basic, well, I guess your advanced algebra graphing class. Okay, so there it is. This is my rectangular equation. It just means an equation that only is involved with x and y variables. You've totally eliminated the t or the theta.